Today we're going to look at lesson 6.3. It's called Applications of Normal Distributions. And our objective for today is to use the standard normal properties to evaluate and analyze distributions that are normally distributed. But today what we're going to have is normal distributions, but they're not necessarily going to be standard normal. And we have to take the material that we did in lesson 6.2 and we'll apply it in lesson 6.3. So a quick reminder of what we did yesterday is we worked with standard normal distributions. So let's take a look here real quick. Remember we had a normal distribution, that was our bell-shaped curve. And for it to be a standard normal distribution, we said that the mean was 0 and that the standard deviation was 1. And what we did is we converted back and forth between z-scores. So we have a z-score of, let's say, 1.96. And then we look to see, well, what is the area under the graph to the left? We worked with areas to the right. We worked with boundaries. We did a lot with looking at a z-score and a probability, and then vice versa. Remember that probability was just the area under the curve. That would be in blue here. So the probability or the area underneath the curve. So today we're going to have distributions that are normally distributed, but they aren't standard normal. So let's take a look at a real quick example, and then we're going to just kind of work through some problems to show how to apply what we're going to do. So let's say IQ scores. IQ scores are normally distributed. Generally, they have a mean of 100 and a standard deviation of 15. So instead of having a mean of 0 and a standard deviation of 1, in a real problem, an application problem, we have a mean that would be some kind of a value and a standard deviation of some value that generally aren't 0 and 1. So what we have to do in this section is convert everything into standard normal so that we can look at standard z-scores. And we're going to use a formula to do that. And that is, in order to find the z-score of a distribution that is normally distributed, we are going to use this formula that we take the random variable x, we're going to subtract that from the mean, and we're going to divide it by the standard deviation. So for example, in the IQ example, if we wanted to know what is the z-score associated with an IQ of, let's just say 120. So you take an IQ test, you get a score of 120. Where does that place you on the standard normal curve? Well, this would be our random variable x. So the z-score would be 120 minus the mean. And for our IQ problem, the mean is 100. And the standard deviation, sigma, is 15. So our z-score would be 120 minus 100, or 20, over 15. And if we went to put that into a decimal number, we would get 1 and 5/15, or 1.3 repeating. So an IQ score of 120 would have a standard z-score of 1.33. So that kind of begs the question, a z-score of 1.33, what percentile does that put you in? Well, we can go to, let me bring this up. We can go to our normal distribution calculator, and we have a z-score of 1.33. We're looking for the cumulative probability. Remember, that would be left of 1.33. The mean is still 0. Standard deviation is still 1 because we converted it to normal. And that would put us in about the 91st percentile. So the cumulative probability less than 1.33 is this 0.90824. So an IQ score of 120 would be better than almost 91% of the other people that took the exam, took the IQ test. So we said one of the main things we're going to do in this section is apply the standard normal distribution. So let's take a look at this problem of why do doorways have a height of 6 feet 8 inches. The typical home doorway has a height of 6 feet 8 inches or 80 inches. Because men tend to be taller than women, we will consider only men as we investigate the limitations of that standard doorway height. Given that heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches, find the percentage of men who can fit through the standard doorway without bending or bumping that height. That'll be our first task. We want to then evaluate or interpret, is that percentage high enough to continue using 80 inches? And will a doorway height of 80 inches be sufficient in future years? Okay, let's explore this. What do we know? Well, in the problem, we know that we have a mean of 69.0 inches and a standard deviation of 2.8. If we want to find the percentage of men who can fit through the standard doorway, we need to find a z-score. So then we can use that z-score and find the area underneath the normal curve. So we're going to use our conversion formula, that z equals our random variable minus the mean divided by the standard deviation. So in this problem, our random variable, what we're looking at is our 80 inches. That's the standard doorway. So we'll take 80 minus 69 divided by 2.8. So 80 minus 69 is 11. And 11 divided by 2.8 to get our z-score is 3.9. I'm going to go ahead and round that to 3.9285. We'll say 3.93. So now that we have our z-score of 3.93 graphically, we've got our normal distribution. Our z-score of 3.93 is going to be way out here. I mean, that's a really high z-score, and that's going to be an unusual height of 80 inches. So if we go to our normal distribution calculator, and we're going to put in a z-score of 3.93. Sorry, I'm trying to punch all these numbers in. Now we need to get rid of the probability there. Let's just delete that section. And let's calculate. So we get a cumulative probability of 0.99996. 0.99996. That is the area underneath the curve and left of a z-score of 3.93. So let's use that number to interpret or evaluate the question. So what percentage of men can fit through the door? Well, in a percentage, that's 99.996%, so dang near 100%. Is that percentage high enough to continue using 80 as the standard height? Well, I would say yes, that nearly 100% of the men will fit through that door based on our data. And will a doorway height of 80 inches be sufficient in future years? Now, we kind of have to interpret that a little bit. I would say yes, it would be, but the heights of men are increasing over time. I don't know that they're increasing at a rate fast enough that we should worry about that 80 inches. So I would say that it would be sufficient to use in future years. Let's take a look at another situation. Birth weights in the United States are normally distributed with a mean of 3,420 grams and a standard deviation of 495 grams. The Newport General Hospital requires special treatment for babies that are less than 2,450 grams. They would be considered unusually light or unusually heavy, and that would be greater than 4,390 grams. What is the percentage of babies who do not require special treatment because they have birth weights between the 2,450 and the 4,390? That's the first question. The second is, under these conditions, do many babies require special treatment? So for our problem, we have a mean of 3,420 grams, a standard deviation of 495. What we want to look at is we want to get two separate z-scores. We want to know our unusually light babies, and that is a weight of 2450, so we want the z-score associated with that one. And our usually unusually heavy babies that weigh 4390, so we want the z-score associated there. So we have to find these two different z-scores. So the z-score associated with 2450, so we take 2450 minus the mean, 3420, divide it by 495. That'll be one z-score. The other one will be the unusually heavy babies, 4390 minus 3420, divided by 495. So we want to evaluate both of these. When we evaluate those, the first one, 2450 minus 3420 is minus 970 divided by 495, and we get a negative 1.96. And when we do the z-score on the right, we get plus 970 divided by 495. That equals positive 1.96. So the z-scores that we're working with right here, that z is negative 1.96, and this one, the z-score is 1.96. So let's evaluate that z-score of 1.96. And punch that in, 1.96. Let's get that going, and we'll calculate it. So the positive 1.96 is 0.975. What I want to do is look at the negative 1.96 first. And let's see what happens when we punch that minus sign in there. When we put the z-score as negative 1.96, we get a cumulative probability of 0.0250. So let's take a look at that on the graph. So 0.0250 is going to be the area here, 0.0250. From what we know about the symmetry of a normal distribution, then the area to the right of this one is 0.0250 as well. Or actually, that was 1 minus that 0.9750 that we came up when we put positive 1.96 in there. So the question says, how many babies do not require special treatment? So we're actually looking for, we'll have to do another color, but we're looking for the area in green that's between these two. That's the percentage that we're after. So it's easier for us to look at what's not in there. So if I take 0.025 and add it to 0.025, I get 0.05, leaving me 0.95 in the green area. In other words, 95% of the babies do not require special treatment. So if we look, sorry about that, if we look at this under these conditions, do many babies require special treatment? Actually, not very many. Only 5% of the babies require special treatment. That's going to be these two. So we answered both parts of it. How many babies do not require special treatment? 95% do not. How many do require special treatment? Well, it's the complement of that, or 5%. So the last problem I want to look at is a little bit different. It says when designing an environment, one common criteria is to use a design that accommodates 95% of the population. So we'll look at doorways. How high should doorways be? It should say if 95% of men will fit through without bending or bumping their head. That is, find the 95th percentile of heights of men. Heights of men are normally distributed with a mean of 69.0 inches and a standard deviation of 2.8 inches. So in other words, we've got a mean of 69.0, standard deviation is 2.8. And we want to find what height we should build the doorway. So we don't have this random variable x right now. Because remember, we've been using this formula, x minus mu divided by the standard deviation. And what we're after is we're wanting to find this number. We're wanting to find that random variable x, the height of the doorway we should build. So we know mu already, and we know sigma. We need to get this z-score so that we can solve for x. So graphically, what we're looking for, there's a normal distribution. We want to know what is the z-score here such that 95% of the men can fit through the doorway. We want the area to the left of this to be 0.95. So we're going to go back to our calculator, and I've already plugged it in. We want to know what is the z-score associated with a probability of 0.95. And if we calculate that, we get a z-score of 1.645. So if we come back over here, now our z-score is 1.645. So 1.645 equals x minus mu, which is 69.0, divided by the standard deviation of 2.8. And in order to solve for x, we're going to need to cross multiply and solve. So 1.645 times 2.8 is 4.606, and that equals 1 times x minus 69.0. If we add 69 to both sides, then we get x to be 73.606. Let's go ahead and round that to 73.6 inches. So 95% of the men are going to fit through a doorway that is 73.6 inches. So let's evaluate that, interpret that just a little bit. 73.6 inches. If we put that into feet, well, 72 inches would be 6 feet. So it's 6 feet and then another 1.6 inches. 95% of the men would fit through a doorway that size. But do we see a problem with that? I'm sure we can all think of people who are over 6 foot 1.6. In fact, Kyle Rourke, you're 6'3" or 6'4", you wouldn't be able to fit through this doorway. So just because 95% of the men fit through it, I don't think it has a realistic or a practical application. I just think that doorway is a little too short. Just because 5% is a big number. If we think of that, you know, that's 5 out of every 100 or 1 out of every 20 people, men especially, 1 out of every 20 men won't be able to fit through this doorway. So although it fits our data, it doesn't have a real practical value. And that's why in the first problem, we use that standard doorway of 80% or 80 inches because nearly 100% of the men fit through that. All right, quick recap. In this lesson, we took and used normal distributions and we converted them to standard normal distributions so that we could find z-scores and find percentages and find probabilities. And remember, the formula that we are going to use the most in here is to find the z-score of a normally distributed set of data is the random variable minus the mean of the set of data divided by the standard deviation of the set.